I've got a bag of candy and I'm interested in knowing how many pieces are in it. How do I do that? Well, I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. But there's a particular number system I'm using to count there. I'm using the base 10 system, the decimal system. Computers don't use the base 10 system. Instead, they use binary, or base 2. That's because it's an electrical system and can only use a 1 or a 0, an on or an off. So computers use binary, but that creates some very unwieldy numbers. As a result, we want to be able to work in the octal and hexadecimal number systems as well. So that's what we'll tackle here. We're looking to understand how the binary, octal, and hexadecimal systems work. To do that, though, we're going to start by reviewing what we know about the decimal system. In the decimal system, we have 10 symbols available to us. They are the symbols, or the digits, 0 through 9. These are the only ones that we can use, and we have to create all numbers using only these 10 symbols. We go beyond the number 9 by using place values. So I've got my bag of candy, and I'm counting how many pieces are in it. Before I get started, I have 0 pieces of candy. I pull out the first one, and I record that as a 1. Pull out a second, third, fourth, fifth piece, and I have 6, 7, 8, and 9 pieces of candy that I've counted. When I pull out one more piece of candy, how do I represent that? I only have 10 symbols and I've used all of them. But so far they're all in the ones place value. So I flip my 9 back to a 0 and start over, and I increment the place value to the left by 1. So we understand the first column here to be the ones place value. We're counting by 1. In this second column, I'm no longer counting by 1. I'm counting how many groups of 10. I'm counting by 10. So I've pulled my 10th candy out of the bag and recorded it as a 1, 0 in the decimal system. My next piece is, of course, 1, 1 or 11. After that, I have 12, 13, 14, 15, 16 pieces, which, just to recap, means I have 6 individual pieces and one group of 10 pieces for a group of 16. Then 17, 18, and 19 pieces. When I pull out my next piece of candy, how do I record that? Well, I now have 2 groups of 10. So in the ones place value, I scroll back to 0, I roll the place value back to 0, and I increment the place value on the left by 1. I now have 2 groups of 10 and no additional groups of 1. At some point, I'll fill both the ones place value and the tens place value with 9s. I have 99 pieces of candy. I pull out one more piece. It's a very large bag of candy. And my 9, I have no choice but to scroll that back to 0 and increment the place value to the left. So my 9 in the ones place becomes a 0, but the same thing happens in the tens place. I also roll that back to a 0, and I'm going to increment the place value to its left by 1. How many items does that 1 represent? Well, that now represents 100 items. We are counting in this place value by 100. So if we know how to count in base 10, then we can deconstruct a number that we're given. Kind of do the opposite. We're given the number and asked what it represents. Here we're looking at the number 347.08. And you'll notice there's a small subscript of 10 here to tell us definitively that we're working in the decimal system, the base 10 system. How do we understand this number? It's got a digit of 3, then 4, then 7, And then we encounter the decimal point. This is called the decimal point because we're in the decimal system. More generically, this is known as the radix point. After our decimal point, we have a 0 and an 8. What does the 3, the 4, the 7, the 0, and the 8 represent? Well, the 7 is in the ones place value. It represents 7 pieces of candy, or whatever it is that I'm counting. We can write this as the 10 to the power of 0 place value. Recall that 10 to the power of 0, anything to the power of 0, is equal to 1. The 4, on the other hand, is in the tens place value. It represents 4 groups of 10. Write this as the 10 to the power of 1 place value. The 3, it's in the 10 to the power of 2, or the hundreds place value. The 0, well, if I follow this trend, the 0 is in the 10 to the power of -1 place value. What is 10 to the power of -1? Well, the negative exponent tells me to take the reciprocal, so it's 1/10. Or if you prefer decimals, 0.1. So the 0 is in the tenths place value. And it follows that the 8 is in the 10 to the power of -2, or 1 over 10 squared, which is 100, or 0.01, the hundredths place value. So how do we read 347.08? We recognize that since the 3 is in the hundreds place value, we have 3 groups of 100, just 3 hundreds, 300. We have 4 groups of 10 for a total of 40. We have 7 groups of 1 for a total of 7. Then comes the decimal point. We have 0 groups of tenths, which is still 0, and 8 groups of the very small hundredths, which is 0.08. If we add up 347, 0, and 0.08, we return to the original number of 347.08. Again, this is a value in base 10. When we do this exercise in base 10, it's fairly circular, but we're going to use this exercise to read numbers written in other number systems. And the first number system we'll look at that's different from the decimal system is base 8 or octal. In base 10, we had 10 symbols, 0 to 9, available to us. In base 8, we have 8 symbols. They are the symbols or the digits 0 through 7. So 8 and 9 do not exist in this number system. So how do we count pieces of candy? I'm going to take the same pieces of candy out of my bag and count them, but do so in the octal system. I'm going to compare my octal numbers to the decimal counts in each case. So my first number I'll record is the one before I get started, when I have 0 pieces of candy. When I pull out my first piece of candy, I'm going to write that down as a 1. Second, third, fourth get the same treatment. Now I have 5, 6, and 7 pieces. When I pull out my 8th piece of candy, that's really only an 8 in the decimal system. In octal, we've run out of symbols. What do we do when we run out of symbols? Again, we've been working in the ones column, in the ones place value, so we roll back to the beginning and we increment the place value to the left. How do we understand these two numbers? Again, the column on the right here is the ones place value. This is where we're counting by 1. The column to its left, however, which was a 0 all the way along in the first column, and where we now see a 1, well, this 1 represents a group of 8. In the octal system, in the second place value, we are counting by 8. Let's keep going. Pull out another piece of candy, and I have 1 pieces of candy, equivalent to the decimal number 9. And then 1, 2, 13, 14, 15, 16, 17, and I've run out of symbols again in the ones column. That's okay. I flip the ones column back to the beginning, back to 0, and I increment the place value to the left, the eights column, the eights place value by 1. So my 1 turns into a 2. So to be clear, this 2 represents 2 groups of 8. I can keep going, and at some point, I'm going to hit my maximum in the ones column and in the eights column. So I have 7 pieces of candy. We'll talk about in a minute how many places of candy this is when counted in decimal. In any case, I have my 7 octal pieces of candy, and I add 1 more to the pile. So I increment the ones place value by 1, but I'm out of symbols, so it rolls back to a 0, and I increment the place value to its left, but since it's also already maxed out at the 7, it rolls to a 0 again, and I increment the next place value to its left by 1. How many groups does this 1 represent? We're going to answer that question on the next slide. We'll do that by exploring this number, 257.13. We see a small lowercase 8 to identify this as an octal number. I see the digits 2, 5, 7, followed by a point. And because this is the octal system, specifically, we can call this the octal point. Again, more generally, the radix point. Following the octal point, I have a 1 and a 3. Where do we find each of these digits? What place value is it in? Well, the 7 was in the 1's place value. Because this is the octal system, I'll write this as 8 to the power of 0. So we have 7 1s. The 5, on the other hand, that was counting in groups of 8. That's in the 8's place value, the 8 to the power of 1 place value. And the 2, that's in the 8 to the power of 2, or the 64's place value. Following the same pattern as previously, that tells me that the 1 is in the 8 to the power of negative 1, 8 to the power of negative 1, or in the 1/8 place value, and the 3 is in the 8 to the power of negative 2, or 1 over 8 squared, 1 over 64, it's in the 64th place value. So to understand this number in the more common decimal system, we read the digit and multiply by its place value. So we have 2 groups of 64, 2 groups of 8 to the power of 2, or 128 items, 5 groups of 8 to the power of 1, or 5 groups of 8, so that represents 40 items counted in base 10, 7 groups of 1, which is just 7 items, 1 group of 8 to the power of negative 1, or 1/8, so 0.125, and 3 times 8 to the power of negative 2. That gives us the slightly ludicrous number, 8 to the negative 2 of 0.046875. 128, 47, 0.125, and 0.046875 are all numbers in the decimal system. Also, because they're in the same system, I can add them up. That gives me a total of 175.171875, and I'll indicate clearly that this is a number in base 10. So what we've done is we've deconstructed the octal number 257.13 into its value in the decimal system. Essentially, we've done our first conversion between number systems. So let's move on to the hexadecimal system, or base 16. This time we have more than 10 symbols. Base 10 had 10 symbols, 0 through 9. Base 8 had 8 symbols, 0 through 7. And base 16, we're going to need 16 symbols. So we start with 0 through 9, but then we need a unique symbol for the numbers 10 through 15. So we use the first 6 letters of the alphabet, A through F. Let's count the same number of items, pieces of candy, in the bag. Again, I'm going to compare each value to the decimal system. Before I start counting, I have 0 pieces of candy. I pull the first one out of the bag and I have 1 piece of candy. Then 2, 3, 4, 5, 6, 7. 8 is a symbol that exists in hexadecimal, as is 9. Then when I pull out 1 more piece of candy, I have a symbol for that. I say that I have A pieces of candy, and then B, which corresponds to the decimal number 11. Finally, C, D, E, and F. Now I've used all 16 symbols. So when I add 1 more piece of candy to the pile, I pull 1 more piece of candy out of the bag. Well, I have to take that ones column, flip it back to the beginning to 0, and I increment the place value to its left by 1. Again, this first column in all 3, or the first one on the right-hand side, that's the ones place value. Here, I'm counting by 1. In the place value to the left, in other words, what does this 1 represent? Well, in this place value to the left, I'm counting by 16. That's one group of 16. I can keep adding to it. Now I have 1 pieces of candy, 1, 2, and so on. Eventually, I reach 15 in both the ones column and in the 16s column. When I pull 1 more piece of candy out of the bag, I'm going to have to increment the ones place value by 1. However, because I'm already out of symbols, I flip it back to 0 and I carry or increment the place value to its left by 1. Well, it's at its maximum as well, so it rolls over to 0 and I increment the place value to its left by a final 1, from 0 to 1. Again, my question for you is, what grouping is this? What are we counting by? How many items does that 1 represent? Let's take a look at a final number, 3A9.B1. This number is in base 16. So I have the digits 3, A, and 9, and then we can call this the hexadecimal or the hex point, or again, more generally, the radix point. Following the radix point, I have the digits B and 1. The 9 is in the ones place value. I have 9 items as I normally understand them in base 10. This is in base 16, the 16 to the power of 0 place value. The A, which is our stand-in for the decimal number 10, that's in the 16's place value. And the 3, that's in the 16 squared, or the 256's place value. It gets a little bit ridiculous. The B, our stand-in for the decimal number 11, if we follow the pattern, must be in the 1/16 or 16th place value. And it follows then that the 1 is in the 16 to the power of -2 or 256th place value. So that's the number in base 16 and the place value we understand for each digit. What does that do? It allows us to read it into decimal. We have 3 groupings of 256, or a total of 768 items. A is the stand-in for decimal number 10, so we have 10 groups of the 16's place value, 10 groups of 16 for a total of 160 items, and then 9 groups of 1 for 9 items. Following the radix point, we've got B, or 11 groups of 16ths, 16 to the power of -1 for a total of 0.6875, and 1 times 16 to the -2 for a very small number, 0.0039065. Again, the 768, 160, and the 9 and the 2 decimal values are all in base 10, so I can add them together, and I get a total of 937.6914065. So I've read the base 16, the hex number 3A9, point B1, into decimal. So I'll be clear about that with a subscript of 10. And finally, we reach the true computer number system, the base 2 system, or binary. Binary is pretty awkward. We only have 2 symbols, 0 and 1, that we're allowed to use. There is no 2, there is no 3, there is no 4 in the binary system. Again, I'm going to compare, as I count pieces of candy, the numbers in binary with the numbers in decimal. Before we start, I have 0 pieces of candy. I take 1 out of the bag, I have 1 binary piece of candy. When I take a second 1 out of the bag, second or 2 as I understand it in decimal, and I go to write that in binary, I've already run out of symbols. So the 1 flips back to a 0, in other words, we start over, and we increment the place value to the left. When I add piece number 3, I can again increment the 1's place, and the place value to its left is still a 1. My 4th piece, I'm already out of symbols again. 1 flips back to 0. I increment the place value to the left, but it's already a 1 as well. So it flips right back to the beginning, and I increment the place value to its left. Which place values are these? Well, my first column here, this is my 1's place value. In other words, where I'm counting by 1's. In the second column, think about what that 1 represented. Well, here I'm counting by 2's. This is the 2's place value. Counting by 2's. What am I counting by here? Hopefully you see the pattern by now. Otherwise, we'll make it clear on the next slide. In any case, I'm going to keep going. My next piece gives me 101. Then 110 and 111. If I add one more piece, each of the 1's in the first 3 columns flips back to a 0, and I have to add a 4th place value. This is the 8's place. Then I follow with 1001. 1010, 1011, 1100, 1101, 1101, 1110, and then 1111. Take a moment and have a look at the table we've just constructed. And maybe it helps us to fill in or to pad the numbers on the left with 0 so that each of the 16 binary numbers from 0000 to 1111 has the same number of digits. What patterns do you notice? One of the patterns that I see is using the first 2 digits, the 1's and the 2's column. I have a repeating pattern of 00, 01, 10, 11. Now I incremented the place value to the left and I started again. 00, 01, 10, 11. You'll find lots of patterns like this. You can also think of this in terms of vertical patterns. The ones place alternates 0, 1, 0, 1, 0, 1, 0, 1. The twos place has 2 zeros followed by 2 ones, and then 2 zeros followed by 2 ones. What happens in the fours place, where we're counting by groups of 4, counting by fours? We've got 4 zeros, 4 ones, 4 zeros, 4 ones. The most important pattern that I want us to see, though, is how many binary places it takes to count through our decimal numbers. If I allow myself only one binary place, only counting by ones, then I can count 2 numbers, 0 and 1. So again, I'm in the binary system. I have 2 options, 0 and 1. If I allow myself only one binary place, I can count 2 numbers. If I allow myself 2 binary places, notice that I can count all the way from 0 to 3. Using 2 binary places lets me count to here. So 1 binary place got us to 1 or 2 numbers. 2 binary places gets us to 3 or 4 numbers. Again, we're in the binary system. So we have 2 options, a 0 or a 1. And I've given myself 2 columns. So I can count 2 to the power of 2 or 4 numbers. If I allow myself a 3rd place, I get quite a bit further. Using 3 binary places, I've been able to count from 0 all the way through to the decimal number 7. We're working in binary. I have 2 numbers, and I've given myself 3 place values. So I've been able to count 2 to the power of 3 or 8 numbers. Is this starting to look familiar? In the octal system, we were able to count from 0 to 7. So if I replace the heading here with octal, this table would still be true, at least the one on the left. What happens when we move to the right? Well, now I've allowed myself 4 place values. If I have 4 place values, I don't max them out. I don't have a 1 in each until I get to the decimal number 15. Maybe instead of thinking of this as decimal numbers, that 15 feels familiar as a hex number. Only then we wouldn't write 10, we would write A, B, C, D, E, and F. So using 4 place values, again, because we're in the binary system and have 2 options, and 4 place values gives us a total of 16 combinations. So when we had 3 place values, we had 8 combinations, or we were able to count from 0 to 7. When we have 4 place values, we have 16 combinations. In other words, we're able to count from 0 to 15. Or, in the hexadecimal system, from 0 to F. So what I'm getting at here, and what we'll see in a bit as we convert between binary, octal, and hex number systems, is that while binary numbers get very unwieldy, we can easily convert them to octal or to hex numbers. And these are a very human-friendly way to communicate binary numbers.